Good evening, everyone. I'm Jun Yao. I come from Southwest Petroleum University, Chengdu, a beautiful city of China. Here, at first, I appreciate Vebleo for their invitation. It's my great honor to attend this meeting and have the opportunity to communicate with the counterparts over the world. Today I talk about advanced materials and photoelectrochemistry. My presentation divided into 4 parts. I am reserve candidate for academic and technical leaders in Sichuan province, and I lead the high-level construction team of Southwest Petroleum University. This is my research direction: FR, EC, PEC sensors, nanomaterials. This is my partial publication, nearly 10 years. Monitoring based on principle of FR. It has many advantages such as simple method, simple equipment used, and fast speed, sensitivity, selectivity, and stability is limited as 3S for scalar, which is very important for sensor. However, it has many disadvantages, including low sensitivity, low selectivity, and terrible stability. This is my related publications published in Chemical Review at 2014. Combination of FR and nanotechnology greatly expanded their range of application. In my team, we studied various nanomaterials, include quantum dots, carbon quantum dots, gold nanoclusters, MOFs. Their size are from 10 to 1,000 nanometers. We introduce radiometric FR technology to enhance significantly the stability of the sensor. In this study, we constructed the bimetallic MOFs and the 9 enzyme to improve the sensitivity of the sensor. And we introduced radiometric FR technology to enhance the stability of the sensor. In nature world, the enzyme is very efficient. Based the viewpoint, we develop the doped MOFs as the nano enzyme. This is the SEM TM of the doped MOFs. From this picture, we can see the doped MOFs is in rod-like structure with prismatic tips. The TM shows that the doped MOFs own spatial layer and packed structure. This is FTIR XRD. From FTIR, we can speculate the functional group of this material. From the XRD, the doping of AS metal only slightly changes the presentation of diffraction peaks, proving the crystal structure still maintains the same with the former ones. The optimized structure of the pure MOFs and the doped MOFs were simulated by DFT study. This one shows the cholesterol and its oxide broad doped MOFs or FR intensity increase at 458 nanometers. (615 nanometers). Cholesterol and its oxides will be react to produce the hydrogen peroxide, which can quench the Fl single of the ZS metal, and the hydrogen peroxide will be clustered by the doped MOFs to produce the hydroxyl radical. The hydroxyl radical will increase the single of TPA linking. We use the ratio of the above FL peaks intensity to monitor the cholesterol. This is the density of state and the partial density of state of different centers in different MOFs. From this picture, we want to choose the best detection condition, such as enzyme, dose, and time. This one is FR single with the increasing concentration of cholesterol. From this picture, we can see for AM detection between EU, they are MOFs with dual band, luminous. There are another 4 studies. This one is optimer FL sensors for ATP monitor. This one developed a coaxial QDS, and this one is a AFM optimer FL sensors, both for micro eyes. This one is a GQDS FL sensors for determinations of copper ions and MPG. Part 3, EC sensors. EC has advantage: low cost, high precision. We will introduce molecule imprinting technique. We will combine the EC and MIT into one system based all-in-one viewpoint. We constructed bone nitride, fluorine, carbon, quantum dots, silver nanoparticles, as dual amplification signal, which can enhance significantly the sensitivity of the sensor in order to promote the selectivity of the sensors furtherly. We introduce MIP technique. This scheme is a step-by-step fabrication process of the sensor. We synthesize BNF CQDS through hydrothermal method. We put the glass carbon electrode in the silver nitrate solution to prepare silver nanoparticles modified GCE through electron deposition. We drop the BNF CQTS on the surface of a bar modified GCE, and then put the co-modified GCE into pyro and BPS to carry out the electron polymerization. Finally, we use organic solvent to remove the target molecule. So the MIP BNF CQTS silver nanoparticle co-modified GCE was obtained successfully. This is SEM, TM, UV absorption, FR, and FTIR, XRD, FESEM of above materials. This is SEM AFM of MIP. From the AFM, we can calculate the film thickness is 136.3 nanometers. This is a sensing mechanism. This is EISCV ASV curves. According to the related equation, we can calculate many parameters such as Petroleum number, electron number, active area of electron, diffraction coefficient. The result shows the active area of modified electrode is bigger than that of bare electrode. This is calibration curve. This is condition optimization. The base pH of the system was chosen as 5. In order to evaluate the selective recognizability of the sensor, 5 chemical reagents with similar structure or function group to BPS were selected as computers. They had no considerable effect on the performance of proposed sensors for the detection of BPS. Table 1 is the current case of BPS. Table 2 is the detection of BPS in real samples, such as mineral water bottle, disposable paper cups, and droppers. There are other three easy sensors. We develop different QDS easy sensor for different target molecules, such as BPA, BPS, LCYS. Part 4, PEC sensor. Whether are there more tactics to improve 3S extremely? We combine the photon and EC into one system. In this study, we constructed copper oxide coated silver graphite carbon nitride cadmium sulfide nanocomplex heterostructure, which can increase the sensitivity, and we introduce the antibody 1, antibody 2 to establish a sandwich type mode. Which can specific recognize the CA. This scheme is the construction process of the sensor and the probe mechanism. Firstly, drop the graphite carbon nitride on the surface on the ITO. Secondly, added the cadmium sulfide QDS on the modified ITO. We use EDC NSH to anchor the antibody 1 through gold sulfide bond, and then the CA was added into this system. So these nanocomplex materials can specifically recognize the antibody 2 modified copper oxide coated silver. We can monitor the CA concentration through the change of PEC single in the bio process. There are some characterization, including TEM, SEM, UV absorption, XRD, XPS, EIS, this is the photocurrent signal with the increasing concentration of CEA. From this picture, this sensor can specific recognize toward CEA. The scheme is the photocatalysis mechanism. The scheme displays the VB and CB. The result displayed in the detection process of AA is illustrated system. How hydrosol radical how to use and the way the electron how to transfer is demonstrated deeply. In all, our group developed 3 STEM sensors, including FA, EC, and PC sensors for various emerging applications in the life environment and energy fields. We appreciate NSF Science Technology Department of Sichuan Province, Sichuan University, and China West Lomo University. This is my group. Thank you, my partner. Thank you, my dear colleagues and friends of you. Thanks for your attention again.